In the modern era of aerospace engineering, aircraft design and operation are deeply dependent on digital computation across modeling, simulation, control, and diagnostics. Yet in recent years, an unsettling trend has emerged. Aircraft components are failing more frequently, from minor anomalies in control surfaces to catastrophic structural fatigue. It begs the question, why are planes falling apart? While it's tempting to attribute these issues to isolated manufacturing defects or maintenance oversight, a deeper systemic issue is at play. The increasing reliance on high-precision digital systems that interact with continuous analog reality introduces subtle but accumulating inaccuracies. These inaccuracies, rooted in the limits of digital representation, can cascade through systems in ways that are difficult to detect until failure occurs. At the root of these issues lies a fundamental incompatibility between the continuous mathematics that govern the physical world and the discrete approximations used in digital computation. Engineering constants such as pi, phi, and functions like sine and cosine are integral to modeling stress, vibration, and rotational dynamics. Yet these values cannot be represented exactly in a binary system. When encoded in digital form, they are approximated to a fixed level of precision, often using IEE floating point standards. These approximations, while appearing negligible in isolation, can produce systemic deviations when embedded in long-duration simulations or iterative feedback loops, such as those found in flight control algorithms or structural health monitoring systems. Consider the widespread use of pre-computed trigonometric tables and polynomial approximations in avionics systems. These methods are employed to save processing time in embedded systems with strict real-time constraints. However, every lookup or interpolation substitutes a smooth, continuous function with a piecewise or truncated representation. In systems that rely on high-accuracy phase or rotational symmetry, such as inertial guidance or flight stabilization, this can introduce micro-errors in angular calculation. While these errors are individually small, they become compounded over time and space, particularly in tightly coupled control loops. In a plane flying thousands of hours under dynamic stress, this accumulation becomes non-trivial. These small computational deviations don't simply stay confined to one subsystem. Aircraft are examples of tightly integrated multimodal systems where structural, thermal, and mechanical domains are interdependent. This interdependence forms a logical triad of reinforcement and feedback, where small imprecisions in simulation lead to slightly off predictions, which lead to marginally incorrect actuation, which feeds back into the model as empirical confirmation. The system reinforces its own drift, masking the divergence until the modeled behavior no longer matches reality. At that point, diagnostics may flag anomalies, but the root cause, misalignment between encoded models and physical dynamics, remains invisible. From a systems logic standpoint, we are seeing the consequences of harmonic breakdown. Engineering design assumes a coherence between modeled parameters and physical performance. When that coherence is disrupted by cumulative approximation error, the triadic structure shifts from harmonic, where each part reinforces and validates the other, to dissonant, where deviation in one part implies divergence in the others. The aircraft may still believe it is flying within spec, while in fact it is operating under conditions that subtly violate fatigue tolerances, aerodynamic balances, or structural resonance limits. This is especially critical in edge case environments, high altitude, high speed, or variable load conditions where tolerance bands are narrow and unforgiving. Quantum engineering, in its emerging role, pushes this boundary even further. Quantum sensors and materials promise precision beyond what classical systems can offer, but they also amplify the challenge of reconciling digital abstraction with analog complexity. Quantum systems are exquisitely sensitive to small perturbations, making them both powerful and perilous. In aircraft engineering, incorporating quantum-based components without fully addressing the inherited discretization errors from classical digital systems can create a misaligned hybrid, a system that assumes quantum-level precision on one end while carrying forward classical-level approximations on the other. This mismatch can mask the degradation of performance until it breaches a catastrophic threshold. Ultimately, the question of why planes are falling apart is not one of simple error, but of systemic misalignment between the discrete and the continuous, the simulated and the real, the abstract and the embodied. The limitations of digital encoding, particularly when used without full awareness of their logical consequences, can create blind spots in engineering systems that only reveal themselves under stress. As systems become more integrated and interdependent, these blind spots grow more consequential. The path forward requires not just better precision, but a new logic of design, one that understands how digital representations reinforce or disrupt the triadic harmonies that keep complex machines in the sky.